right, so let's take a look at chapter 9.1. So we're going to come back with all of our knowledge of quadratic expressions and expressions in general, using the algebra blocks and kind of being able to make sense of them. Let's come back to the chapter in the textbook and make sure that we have looked at the some of the ideas there. So first of all, what we want to be looking at is how do we actually make sense of expressions, and how do we engage kids in making sense of expressions? Kids see lots of things that don't make sense. Primarily, a lot of the time they see formulas and they just memorize them. They don't feel like the formulas make sense. They don't feel like the expressions make sense, and often it's a mystery where those come from. Well, let's take a look at at a fairly straightforward situation where we can really trace where the expressions are coming from. So, for example, if we're looking at the number of dots in this pattern, we can see that there are groups of dots, and there's a structure to this pattern, right? So all the yellow petals have 3 dots, and all the purple circles have 5 dots, and the green circle inside has 1 dot. So we should be able to write out that there are 4 orange petals, and they each have 3 dots, and there are 6 purple circles, and they each have 5 dots, and then there's 1 green circle, and it has a 1 dot. Right, so that something like that would make sense based on the picture that we have. And then there are other ways to do it as well, but this certainly is one way that we can visualize it. But then for design B, we have the same design, but the dots are labeled in different ways or distributed in different ways. So for example, we have 6 dots in the green petals, in the 4 green petals, and we have 3 dots in the purple circles and 4 dots in the green circle. But we could still write this out: 4 times 6 plus 6 times 3 plus 1 times 4. We can still write that out because we have a structure that we've already noticed. And let's look at design C. Let's see, how many are there in the orange petals? There's 5, and 4 in the purple circles, and 2 in the green circle. So we've been able to write this out. And now let's look at all of these. Do you see that what changes and what stays the same? So what stays the same between design A, B, and C is the shape of the flower. What changes in the design A, B, and C are the number of dots in each of the sections, right? So we can say that in this scenario, the flower stays the same, and number of dots changes. Okay, so let's see by identifying what stays the same and what changes. Let's see if we can make the same kind of identification in the formulas that we have come up with, or in the expressions that we've come up with. So what stayed the same? Do you see that we have the 4 times 3? The 4 came from the fact that there were 4 orange petals. And in fact, there are 4 orange petals here and 4 orange petals in this design C as well. Do you notice that for the purple circles, we had 6 of them throughout in all designs? And the green circle, we had only 1 of them in all designs. So those are the numbers that stayed the same. Now what changed are the number of dots inside each of the petals or circles. So what the green numbers are, parameters, and we've discussed this before. The green numbers are parameters because they're staying the same throughout this particular scenario. If it was a different looking flower, they would be different. But for this particular scenario, the parameters, or the numbers 4, 6, and 1, are going to stay the same. The variables are the dots, and those are going to change from one design to another because that's the way the dots are distributed is what's changing here. But by looking at the different numbers and the different variables here, we can now identify which of the numbers in the formula or in the expression come from the structure, the scenario, or the parameters, and which of the numbers come from the overall changing situation. So we could rewrite this as 4a plus 6b plus 1c, and that would actually make sense because the 4 and the 6 and the 1 are not going to change in this scenario at all. Whereas the A is going to be the number of dots in the orange petals, the B is going to be the number of dots in the purple circles, and the C is going to be the number of dots in the green circle. So let's take a look at how some of these parameters can make sense. So every number here made sense, has a connection to the picture. Let's see if we can do similar kind of thing for other situations. So here's some dots, and we need to write two different expressions to show how many dots there are. And 2 is a really small number. When I do this in class, we come up with 6, 7, 8 different expressions, and everybody sees it in a different way. So I'm just going to pick two of the most common ones that I see, but there's no reason to say that if I didn't show one, then it's incorrect. It certainly can be correct. With lots of different options. So one of the expressions we'll split this rhombus into 4 regions. So in fact, it'll split it into the actual T, or the cross that's in the middle, and then these regions. So what we will look at is that there are 4 of those triangular regions, and they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 each, 10 dots each. Plus, there are 4 of these, 5 dots each. And then there's that one in the middle. Right? So does it make sense where each one of these numbers comes from? There are 4 regions of those triangles. There are 4 little pieces to the cross, and then there's one number, one circle in the middle of the cross. Okay, so that's one way to look at it. Another way to look at it is to say, hey, I see that we can find dots that line up. And if I just look at the dots that I'm highlighting right now in orange, then I see a 6 by 6 square, right? There's 6 rows, 6 columns. So 6 squared. But then they're not, I didn't highlight all of the dots. There's still these pink ones inside, right? They're the ones that are kind of offset a little bit. And those are also form a square. And what size square is that? It's a 5 by 5. So 5 squared. So what's really interesting is that we have 2 expressions that are very different in nature. The second one is using squares. The first one is not, it's using groups. And they're very, very different. And there's lots and lots of other different equations that you can come up with as well. But expressions that you can come up with as well. But here's an example of 2. And both of them make sense on the picture. The practice of kids, experiencing making sense of expressions is really, really important for them, so that they know that there's no leap of faith, that there's no magic in these formulas and expressions that they're given. So let's do number 3 here. Write an expression for the total number of stars in the star design below. Show and explain why the other 2 given expressions are actually true. So let's look at this. Let's look at 10 times 8 minus 2 times 3 squared. Well, I wonder where that comes from. Now, if I start counting, 1, 2, 3, 4, 5, 6, 7, 8. So I see that this is 8 wide. Right, you can count the row in the middle if you'd like. And down it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the 10. So this 10 times 8 seems to be the number of dots, right? So dots in the large rectangle. But do you notice that they're not all there? There's dots missing here, stars missing here, and stars missing here. Well, how many of them are missing? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 3 by 3. Look at that. It's a 3 by 3. And we're going to be subtracting 2 of those. So we can say that we're going to subtract the top right and bottom left corners. And this isn't really dots, this is stars. Stars. All right, so that makes sense. So this is the big rectangle, and we're taking away the top left, the top right and the bottom left corners. How about this situation? 2 times 7 times 5 minus 4 times 2. Where is the 7 and a 5? And why are there 2 of them? Well, I see this is 5, and I see that this is 7. Do you see those? So it would be the rectangle that's 5 by 7 would be this one. But where is the second one? Oh, why are there 2 here? Well, you see that there is another one, but they overlap. So in fact, even though we'll count every star separately, except for these ones inside here, because we'll count those twice. And that's why they're 4 by 2. And that's why we're subtracting one of those. So this is double counted stars. So I'm going to leave you to write your expression of this that's different from the other 2. I'd also ask you to write 2 different expressions for number 4 and see what you can do with that. Be creative. Make sure that whatever expression you write makes sense in the drawing, can be made sense of in the drawing. Now let's take a look at number 5. So we have a really challenging diagram here. And we're told that we need to write an expression for the total number of sticks. So I see this one thing here, this one pattern, right? I see this, and maybe even with these ones. So I see this pattern. You see that? And then there's another one of those. There's another one of those. How many of them are there? There seem to be 6. Right? So there's 6 of those. And then it looks like there are 5 of those. So I can write 6 times 1, 2, 3, 4, 5 sticks plus 5 times 2 sticks. This one and this one. That's 1, 2, 3, 4, 5. Okay. Would that expression make sense? I'm hoping. Now, the stick design above is 6 sticks wide. They're saying, well, okay, this is when it's 6 sticks wide. How would you modify your expression in part 5 if we had to make 2 more, 8 sticks wide? Well, let's see. What were the parameters here and what were the variables? As I add more and more, right? As I add more and more, I'm going to be adding these guys. I'm going to be adding more 5s, right? So that is actually going to be constant in our situation. Those 5 sticks are going to be added every step. And the same thing with this. So these are also constant. So our parameters are the green ones, right? Now, the red ones, the red numbers, 6 and 5, actually have something to do with how wide this pattern is. So when we had 6 sticks This was 6, and this was 5. But now when we have 8 sticks, do you think that we will have 8 times 5? Right? 1, 2, 3, 4, 5, 6, 7, 8. Plus 1, 2, 3, 4, 5, 6, 7. 7 twos. Notice it's the same thing that's happening again. The 5s, the 5 and the 2 are the parameters because that has to do with the actual design, with the way it's structured. And 8 and the 7 is what's changing. Well, what if it was n sticks wide? Right? So not 5, not 6, not 8, not 20, but n. Do you see that we would have n 5s? Right? N of those rhombuses. And we would have one less of the pairs. N minus 1 times the 2. We can write it a little bit more friendly. 5n plus 2n minus 1. Right? Now, the parameters are the 5 and the 2. And then the value, the number of those patterns that we have side by side are the variables, the n and n minus 1 in this case. So I'd like you to finish up question 7 and see if you can draw a stick pattern for the 4 squared plus 4 cubed expression.